Hi everyone. Today we are going to kickstart this course on off-chain computing using TE coprocessors. We'll explore how off-chain computing addresses the limitations of traditional blockchains and enables high-performing, cost-efficient decentralized applications. Imagine running your AI model or processing terabytes of data securely off-chain while retaining all the decentralization and trust guarantees of a blockchain. That's the power of off-chain computing solutions like Marlin's Oyster. So without further ado, let's dive in. Now, personally, before I start to learn about something new, I like to understand what are some of the key things that it solves or how it would make my life easier if I learn it. So let's quickly go over some of the limitations that we have in L1 blockchains to understand why we actually need alternatives to traditional on-chain executions. Firstly, L1s have extremely limited compute power. Ethereum, for example, can only process about 36 million gas per block, which puts a very severe restriction on what we can accomplish from sheer compute perspective. They also lack native support for floating point math. This is because precision and consistency are two key priorities in blockchain transactions, but for us, it's still troublesome. Next, running an AI or machine learning model on chain is practically impossible due to the prohibitive costs that are associated with such complex tasks. Deploying large programs on chain is also pretty difficult due to the small permanent storage limits enforced by smart contracts. There's also no persistent file storage capability, meaning that you can't store files like graphics, audio, or video directly on chain. Blockchain networks also suffer from high latency. Ethereum, for instance, processes only about 15 transactions per second, which is actually a lot slower than a typical CPU. Surprise, surprise, more limitations. Public blockchains, by definition, are public, so they make all data visible to everyone, which is not ideal if you're dealing with sensitive information, because data privacy. Smart contracts are also kind of limited in their access. That is, they can only access data on the chain that they are deployed on. This severely limits the information flow between blockchains, and data is stuck on one chain. There are other limitations as well, such as not being able to pull in data from Web2 APIs, not being able to serve user requests directly, or the inability to run long-running services like web servers. All these restrictions make it very difficult for developers to build complex or privacy-sensitive applications using only on-chain resources. We've been talking for a while now, so let me show you these limitations in play with a real-world example. Imagine we're building a decentralized job marketplace with dynamic matching. In simple terms, it means that the contract needs to match N job seekers with M job postings by comparing relevant skills, locations, and salaries. Now, if N is approximately equal to M, this becomes an O of N square operation. Just take a look at this code snippet. For just 100 users and 100 job postings, this O of N square algorithm could potentially consume millions of gas units, making it extremely expensive to run on chain. The nested loops you see here would need to iterate through each job candidate combination to calculate the match scores. Even a simple matching logic quickly becomes financially infeasible as the protocol scales. This highlights the need for off-chain computing. So now comes the question of what do we actually mean when we say off-chain computing? In simple terms, any computation that is not performed on-chain with its results posted and then verified on-chain is off-chain computing. This approach enables us to build high-performance yet cost-effective applications that would not be possible with pure on-chain execution. Various infrastructures like Oracle networks, dedicated nodes, or specialized hardware and GPUs can perform these off-chain computations. What makes this approach powerful is that off-chain computations provide cryptographic proofs or hardware-based security, like in the case of TEs, to provide guarantees against tampering, all the while maintaining the goodness that we value in blockchain systems. Off-chain computing is not just about speed, it's about unlocking entirely new capabilities. Two primary examples of off-chain computing architectures are rollups and coprocessors. Let's take a look at why rollups are needed and how they actually work. Layer 2 chains use rollups to scale blockchain networks by processing transactions off the main chain and then submitting compressed data back to the Layer 1 blockchain. Rollups maintain a state that differs from their base chains but still inherit the security properties of their layer 1 chain by posting data or proofs back to them. The state in rollups is persistent because it continues to exist and evolve over time as new transactions are processed. This state is also partitioned because it exists separately from the main layer 1 blockchain. Now, let's go over how rollups function in practice. It all starts with users conducting transactions on the rollup chain itself, that is the layer 2. This is where the sequencer comes in. It confirms these transactions and creates blocks on the layer 2. The sequencer, as the name suggests, determines the order in which the transactions are processed. This ordering helps prevent issues like double spending while ensuring that all network participants have the same view of the blockchain state. Now, after the transactions are confirmed, they are bundled together into batches to optimize for efficiency. Now that we have our batches of transactional data, the L2 posts this data or proofs back to the smart contracts on the layer 1. This is how a rollup works in a nutshell. And now you know. Rollups are perfect for target use cases, but they too are fundamentally just smart contracts. Now, rollups are mainly of two types. First are optimistic rollups. The optimistic approach assumes that all transactions are valid unless proven otherwise. There is usually a 7-day window where anyone can challenge a transaction with a fraud proof. Since there are no proofs required upfront, there is minimal computational overhead during transaction bundling, which makes them really fast. They're really easy to work with as well, since they are compatible with existing Ethereum apps. Arbitrum and Optimism are good examples of optimistic rollups. Now, we also have something called zero knowledge or ZK rollups, which uses cryptographic proofs to confirm every transaction upfront. This means that you get near instant finality, but the tech is more complex and requires more compute due to the heavy usage of advanced cryptography. Polygon ZK EVM, Scroll, and Starknet are some of the ZK rollups that exist today. Rollups significantly increase the blockchain scalability by processing transactions off-chain and batching them together. For us developers, that means lower fees, faster confirmations, and more customizable options. All the while, they inherit the security of the base chain that they are working on top of. But there are trade-offs too. Like a lot of the rollups today rely on a single sequencer for transaction ordering, which raises a lot of centralization concerns. Another thing to keep in mind is that each L2 has to post its transaction data back to the main chain as well, which can create bottlenecks and result in higher fees. Moreover, optimistic rollups have waiting periods for finality due to their inherent challenge mechanism. Things like these make setting up a rollup technically challenging, although there are now plug-and-play options that offer rollups as a service, which makes it a bit easier. Now that we know about how rollups work, let's go back to our decentralized job marketplace example to find out how they can actually help us. Heavy competitions like iterating through the candidate job pairs can be offloaded to L2, allowing for frequent rematching as profiles are updated. The same O of n squared operation that would have costed us several dollars on L1 would now just cost us cents on L2, making the dynamic matching feature economically feasible. Now that we have a viable dynamic matching feature, let's try to add an AI-powered resume parsing to our job marketplace. But wait, LLM inferencing is not possible on L2s due to memory and compute restraints. This is where coprocessors come in. So what exactly are coprocessors, you ask? We'll discuss that in the next video. Thank you for attending today's lecture on off-chain computing.